I'm Robert Flake, professor of electrical engineering at UT Austin, and we have developed an instrument, a TDR, time domain reflectometer, which has high resolution for measuring cables. The applications have to do with if you're trying to find faults, if you're trying to just measure the length of the cable, or if you're trying to find the delay of the cable. You could be synchronizing clocks being different at a different position with an interconnect, and we could use this TDR to find out what the delay is very accurately in the interconnect between two clocks. And that's a big step towards synchronizing the two clocks. We have a time domain reflectometer, which we are measuring the time it takes a signal to go down a cable and come back. And we're making a lot of measurements to see the statistics of how repeatable that measurement is. And later on we will take measurements and then cut it a little bit, cut the cable a little bit shorter, and take a second set of measurements and see if we can detect that it's been cut and by how much. This is the arbitrary waveform generator that we're using, and it generates this exponential signal shown here. This is the output, and that goes over here in this channel 1. Channel 1 looks at the looks at the signal as it goes by. We've got channel 1 set at 1 megaohm, so it's basically a voltmeter that we're measuring there. And then the cable comes down here and goes around the coil and ends up at the top up here. That's the end of the cable, a little over 300 feet. We call this our faceplate on our TDR. It has a lot of parameters that we can adjust, and the measurements that we make with the TDR. If we look at it, it's separated in, these are inputs, these are parameters that we input, and these are the measurements, primary measurements over here on outputs. Over here on the inputs, this tells us what scope we're using, and this one tells us how many measurements we're going to be making. It'll be double that, turns out, 60 instead of 30. Another input important is the alpha that we're using in our exponential waveform signal. That's 5 times 10 to the 7th, 1 over seconds. And these two parameters tell us what the low voltage and the high voltage is that we use to actually measure the difference in time between the two signals, the input signal and the output signal. And so if this is 1 volt here, it's actually 2. If it were 1 volt, the 0.25 would be the low value, and the 0.8 would be the high value. But you just correct that by multiplying by 2. And this is the confidence level that we can adjust. When we do an average, we can get a plus or minus confidence interval, and we can adjust the percentage here, and the percentage is 99.9%, which means that the mean is between plus or minus 1 picoseconds with a 99.9% confidence interval. This is the other second mean, and you can see the first mean was 936 nanoseconds and 11 picoseconds, and the second mean of 30 values was 936, and then it's 10 picoseconds. There's only 1 picosecond difference between the two means. And down here we look at what the difference is between the two means, and it looks like it's 1 up here, but actually, more accurately, it's 0.3 picoseconds. The results, the main results that for the measurement, we'll look at this screen over here. That was a total of 60 measurements, and they're plotted here, 60 of them. You see down in the scale on the horizontal, and that's the variation of those 60 measurements. To see what that means, you look at the difference in these scale on the vertical axis. Going between two levels here is only 2 picoseconds. So that's well within 2 picoseconds, all of that data. The actual average of that 60 measurements is 936.0105 nanoseconds. We usually just stop it at the picoseconds, and that's so it's 936 nanoseconds and 10 picoseconds. The standard deviation of the data, not of the mean, but of the randomness of the data you see here, is 2 picoseconds. So that's a very, very repeatable measurement. This is another way of displaying the data that we just looked at. This is the first 30 measurements, a histogram of them, and this is a histogram of the second 30 measurements. And if you look at the horizontal axis here, the difference between this line and this line is 2 picoseconds. So you can see that the range here is something like 936.014, and over here that's 8, so that's 6 picoseconds between here and here. We have a similar scale down below. That's the second 30 measurements, and the final display down here is the average. The red one here is the average of the top one, and the purple one here is the average of the second one, and that's this is the 99.9% confidence interval for the first average, and this is the 99.9% confidence interval for the second average. All we're saying is they're very close. This is the piece that we cut off, and we're going to, in a minute, measure the width of it by a pair of calipers. So this is the measurement of the length of the piece that we cut, and we're measuring the length of the center pin. And up here we see the measurement 0.072 inches. So we've completed the measurement. You can see here the average of the first 30 measurements was 935 nanoseconds, 884 picoseconds. And the second set was 935 nanoseconds, 862 picoseconds. So the difference between the two was 21.2 picoseconds. The equivalent distance, that's coming from this measurement right here, the 21.2 picoseconds. We divide that by 2 because it's going both ways. and then we divide that by our 130 picoseconds per inch, and we come up with an estimate from the TDR that the equivalent length of that cut is 0.081 inches. Now, the next thing is the measurement we saw earlier. The caliper was 0.072. The TDR says 0.081. So we consider the difference between the two as an error, and the difference between the two is 0.009 inches. And if we look at the relative error, 0.009 inches divided by 3,600 inches, which is roughly 300 feet, gives us a ratio of 2.5 times 10 to the minus 6, or 3 parts per million. Now, this is a histogram of the first 30 measurements before the cut was made, and the increments here between the vertical lines is 3 picoseconds. So you can see the distribution of the 30 measurements. We're about 3, maybe 5 picosecond range there. Well, this is the second 30 after the cut, and you can see that the numbers here are smaller, and in other words, it doesn't take as long to go down and back on the cable. And again, these are separated 3 picoseconds, so you can see this thing probably, it's about 2, maybe 6 picosecond range between the two. Now we'll go down below. Here is the before the cut. This is the average, and this is the 99.9% confidence interval for that average. And over here is after the cut, and this vertical line here is the average of that histogram, and this is the 99.9% confidence interval for that mean. And you can see they're well separated.